Gold. Think about it. That incredible shine, its value. It feels so permanent, so fundamental.
Mhm. It's deeply ingrained in human history, isn't it?
Absolutely. It's in our jewelry, our tech, everywhere. But have you ever stopped to ask, really ask, where does it actually come from?
Yeah, because the answer isn't the simple star stuff. It's much more dramatic.
Exactly. So today we're doing a deep dive into that very question, the cosmic origins of gold and other really heavy elements. We're drawing heavily from some great work, especially an article called Where Does Gold Come From?
Right. Part of a larger look at cosmic forging.
Our goal here is basically to unpack some pretty complex astrophysics, find those aha moments, but keep it clear, keep it fascinating, not overwhelming.
Sounds good. And maybe we should start with the basics, just to set the
This
scene.
idea.
Okay, so right after the Big Bang, you get the simplest elements. Hydrogen, helium, mostly.
The light stuff.
The lightest stuff, exactly. Then stars switch on, and through nuclear fusion in their cores, they start forging heavier elements.
Like carbon, oxygen.
Carbon, oxygen, all the way up to iron. That happens over billions of years inside stars. Standard stellar fusion.
Okay, right. But here's the catch, isn't it? If stellar fusion stops at iron,
hmm
then where do the really heavy elements come from? Gold, platinum, uranium. They obviously exist. We have them here.
Precisely. Something else, something much more powerful, must be responsible for creating them. And that was a huge puzzle for a long time.
So what was the first big idea? Didn't everyone think it was supernovae?
Yeah, for decades, that was the leading theory. Supernovae, these massive stars exploding at the end of their lives.
It kind of makes sense, right? Huge explosions, tons of energy.
Exactly. They're incredibly energetic. They throw off vast amounts of material. It seemed like the perfect place for what we call the process.
The RAP process, rapid neutron capture.
That's the one. Basically, you need an environment flooded with neutrons, free neutrons, that can slam into atomic nuclei really, really fast.
Building them up into heavier elements almost instantly.
Correct. Before they have a chance to decay.
Mm-hmm.
And supernovae seemed energetic enough to maybe do that.
There's always a but in science, isn't there?
Yeah, often, yeah. The but here was that when we ran more detailed models, simulations got better.
Okay.
It turned out supernovae just don't have quite the right conditions. They don't actually produce enough free neutrons, and the material isn't dense enough or moving quite fast enough for long enough.
Ah, so the conditions weren't quite extreme enough in the right way.
Pretty much.
Yeah.
The R process couldn't really get going effectively, not enough to explain the amount of gold and other heavy elements we see. So the supernova theory for gold, well, it was largely debunked.
Okay, so if even exploding stars aren't powerful enough, what in the universe is? Where do we look next?
We needed something even more extreme. And the answer, turns out, involves neutron stars.
Okay, neutron stars. Remind us what those are again. Super dense, right?
Unbelievably dense.
Yeah.
They're the collapsed cores left behind after some types of supernovae. Imagine crushing more than the mass of our sun into a ball the size of a city. A teaspoonful would weigh billions of tons. Just mind-boggling density.
Okay, so these incredibly dense things exist. How do they make gold?
Well, not usually on their own. The key event is when you get two of them orbiting each other. A binary neutron star system.
Which must be pretty rare.
Very rare. And over vast timescales, billions of years sometimes, they radiate energy away as gravitational waves.
Ripples in space-time itself, like LEGO detects.
Exactly like LEGO detects. This causes them to lose energy, spiral inwards, closer and closer, until they violently collide and merge.
A neutron star merger. Okay, that sounds energetic.
Extremely.
Yeah.
And this environment, the merger, it's almost perfectly designed for their R process.
How so?
When they merge, they spew out this incredible torrent of material that is extremely rich in neutrons, just a flood of them moving at incredible speeds.
Ah, so you get that dense, fast flood of neutrons that supernovae were missing.
Precisely. It slams into lighter atomic nuclei, rapidly building them up into the heaviest elements. Gold, platinum, you name it. It's like the universe's ultimate heavy element forge.
That makes theoretical sense. But did we ever actually see this happen?
We did, and it was a huge moment for astrophysics.
Tell me about it.
August 2017, the LIGO and Virgo gravitational wave detectors picked up a clear signal from about 130 million light years away.
Okay.
And the signal's profile matched exactly what we expected from two neutron stars merging.
Wow. So direct evidence.
Direct evidence of the merger via gravitational waves. But then, telescopes all over the world quickly pointed to that spot in the sky.
Yeah.
And they saw the aftermath.
What did they see? Light.
Light, yes.
Yep.
An optical and infrared glow called a kilonova. And crucially, the light spectrum, the colors within that glow, had the unmistakable fingerprints of the R process happening.
You could actually see the signature of heavy elements being created.
We could see the radioactive decay of freshly synthesized R process elements, and based on the brightness and how it faded, scientists could estimate the amount of heavy elements produced.
And the amount of gold.
The estimates were, frankly, staggering. Somewhere between 3 and 13 Earth masses worth of gold alone created in that single event.
13 Earth masses from one collision.
Mind-blowing, isn't it? Suddenly, neutron-star mergers went from a leading theory to, well, pretty much the confirmed primary source for most of the universe's gold.
Okay, that feels like case closed. Mystery solved.
Ah, well, almost. Science loves throwing us curveballs.
Of course it does. What was the problem this time?
The problem was timing. Remember, these mergers can take billions of years to happen. The stars have to form, live their lives, go supernova, then the neutron stars have to find each other, orbit, and slowly spiral in.
Right. A very long process.
Very long. But astronomers have observed some really, really ancient stars. Stars that formed very early in the universe's history, maybe less than 1 billion years after the Big Bang.
Okay.
And these ancient stars already contain heavy R process elements, including gold.
Wait. But if mergers take billions of years, how could gold be present in stars that formed so much earlier than that?
Exactly. That's the temporal gap problem. There just hadn't been enough time for many, or perhaps any, neutron star mergers to occur yet.
So mergers explain most gold, especially gold formed later, like ours.
Yes.
But they couldn't explain this early gold. We needed another faster source.
But we needed another source, one that could kick in much earlier in cosmic history.
Okay, the plot thickens again. What else is out there that could do this?
Well, this led scientists to look again at neutron stars, but a very specific, very extreme type. Magnetar.
And magnetars, what makes them different?
They're magnetic fields. They are unbelievably strong. Hundreds of trillions, even quadrillions of times stronger than Earth's magnetic field. We're talking up to 100 billion Tesla. It's almost impossible to comprehend.
Okay, so insanely magnetic neutron stars. Do they merge too?
Not necessarily. But what they do occasionally is unleash these colossal explosions called giant flares. Think solar flares, but ramped up by an unimaginable factor. These flares are so powerful, they can actually blast off pieces of the neutron star's crust that is, again, very rich in neutrons.
Ah, so another way to eject neutron-rich material into space.
Exactly. It creates another, albeit smaller scale environment where the R process can potentially happen.
Is there evidence for this too? Have we seen a magnetar flare make gold?
We haven't seen the gold directly. That's incredibly difficult. But in 2004, there was a giant flare observed from a magnetar in the constellation Sagittarius, about 40,000 light years away.
Okay.
It produced this incredibly bright gamma-ray burst and an afterglow. And within that afterglow, scientists detected clear spectral signatures of radioactive decay.
The fingerprints again.
The fingerprints again, yeah.
Yeah.
Consistent with freshly produced R process elements decaying. So while we didn't see the gold itself, we saw strong evidence that the R process was happening in the ejecta from this magnetar flare.
Interesting. So now we have two potential sources, neutron star mergers and these magnetar flares. How do they compare?
Well, it's a matter of quantity versus frequency and timing. Neutron star mergers, when they happen, produce vastly more gold per event. Remember those 3 to 13 Earth masses?
Right. Huge amounts.
Magnetar flares eject much less material, so they produce far less gold each time, maybe only a tiny fraction of what a merger makes. But magnetars can exist and flare much earlier in the universe than it takes for neutron stars to merge. And they likely flare more frequently overall than mergers happen.
Ah, okay. So mergers are the big later factories, while magnetars are smaller, earlier, maybe more frequent contributors.
That seems to be the picture, yes. Estimates suggest magnetar flares might be responsible for maybe 1 to 10% of the total heavy elements in the galaxy.
So that 10% could be crucial for explaining the gold in those ancient stars before the mergers really got going.
Exactly. It beautifully solves that temporal gap problem. Most of the gold on Earth, the gold formed over the last several billion years, probably came from neutron star mergers. But that earliest sprinkling of gold found in those ancient stars, that likely originated from these earlier, less productive, but still significant magnetar flares.
So it's not one or the other, it's both. A dual origin story.
Precisely. A more complex, nuanced picture than we first thought.
This whole journey from supernovae to mergers, finding a problem, then adding magnetars, it really shows how science works, doesn't it?
It really does. It's not about finding one answer and sticking to it. It's about refining theories as new evidence comes in, disproving old ideas, encountering new puzzles.
And needing better observations like gravitational waves to really crack the case.
Absolutely.
Okay.
Observational astronomy, especially these new windows like gravitational waves, has been completely transformative. We're literally seeing or hearing the universe make these elements now. It's incredible.
So when you look at a piece of gold jewelry or think about the platinum in a catalytic converter, its journey here was unbelievably violent and complex.
Forged in the collision of dead stars or blasted off hypermagnetic ones.
Yeah.
Yeah, it's quite a backstory.
I love that quote from the article. You think a star is just sitting there being dense, and then it throws gold at you.
Yeah, it captures the surprise, doesn't it?
It really does. This whole deep dive just underscores how much is still out there to discover, how even familiar things have these profound, unexpected origins in the most extreme parts of the cosmos.
It's a constant process of discovery. What we understand today is just built on overturning or refining what we thought we knew yesterday.
It leaves you wondering, doesn't it?
And perhaps that's something for you, our listeners, to think about. As we keep peeling back the layers of the universe, what other things that seem simple or settled right now might turn out to have origins just as complex, just as surprising, forcing us to rethink everything all over again?